Hello, Emily. How are you?
Hello, I'm good. How are you?
I'm doing good too. How's your weekend going so far?
About to be stressful.
About to stressful? I know because of the exam coming up on Thursday.
Yeah.
Oh shoot. Um, and I see the study guide that you sent as well.
Yeah.
On Sovolysis, SN1 mechanism.
Mhm.
um SN1 versus SN2, E1 and E2, and then alcohol reactions. So let's get started with that. I think the best way to do this is to look at like your professor's practice exam that's gonna be similar to the exam, and then based off that, I could teach you like the content. Did your professor provide a practice exam for this
Yes.
exam? Uh-huh.
Yes, I would say some of the only thing is, I will provide that for you. Just the only thing is, like, when you actually do take the test, I would
Mm-hmm.
say, like, that's given, like, a very, very basic version of it. You know what I
Uh,
mean? Like, he
yeah.
kind of, I'll put it in right now, but that's what I
Uh-huh.
noticed. He says it's similar, but
Yeah, it's
yeah, you really need to
yeah.
know everything on the
Y-
study.
And at the study list, yeah. The practice exam like is like the simple version of the actual exam.
Yes.
Yeah, dang. Okay, okay. Good to know.
I'll add that on
Mm-hmm.
here.
Okay. Hmm. What do you know about SN1, SN2, E1, E2 so far? Or like are you confused in general or
I'm just confused in general. Like I've been watching a little bit of Chad's prep, but since he has
mm-hmm.
so many videos on it, it's kind of hard to start myself at one video. I started
Mm,
myself in a video, but then I'm confused. I'm like,
mm-hmm.
I don't quite understand.
Right, right. Uh-huh. Okay. Let's see.
Three. Okay. Mm, okay. I
Mm-hmm.
sent the link for the file in the chat and it's sent.
Mm-hmm. Okay.
So that it has the answer key as well, just included.
Yeah. Let me see here. Download. Got it. Okay. Let me paste it forward to my Notability and then we can get started here. Let me see here. Okay. Okay. And then let me email it. Let me share my screen here. Let's see. Well, where are you taking OChem? Like what school?
At Woodland Community College?
Oh, okay, okay. Yeah.
Yeah.
Let's see. Okay. And then let me email this to myself.
Mhm.
We'll go over SN1, E1, SN2, E2 reactions and then do the practice problem. Let's see, Gmail. Yeah,
Mhm.
just taking some time to send over the file to my iPad. Let's see here. But we could go into like 305 today.
Mhm.
Yeah.
Perfect.
Hmm. Okay, let's see.
And the thing is, like for Woodland, there's no like actual like tutors for like chem, like other subjects. Like there is for
Oh,
chem, but not for OChem.
uh-huh.
I guess
Not for okay.
harder for.
Yeah, it's like no OChem tutoring, but there is for general chemistry tutoring.
Yeah, there is.
Yeah.
And for OChem, it's more like they're technically I wouldn't say they're tutors, but they do offer like SI sessions and
Uh-huh.
hours, but everyone's like there to ask questions, so you really don't have one-on-one. Like,
Tutoring for OChem. Yeah,
mhm.
and then you met Revin and Revin was like teaching you like for the previous midterms.
He sits next to me in lecture,
Oh
and
yeah.
I'm just like curious. I'm like, hey, like, do you tutor? Like,
Uh-huh.
hey, I just like need. I noticed because he's a good student.
Yeah.
Like, well, he does EMT, but he recommended a friend that you go to UC Davis, right?
Mm-hmm.
Yeah.
Yeah. Right. Right. Uh-huh. I see. That's good. That's good. Yeah. Okay. Um, so let's get started with this practice exam here, one by one.
Mhm.
Uh, oh, is this the key already? Like the key?
On it without the key.
Uh-huh. Oh, yeah, it's okay. It's okay. We could go over this with the key, and then I could just give you a similar practice problem to this.
Okay.
Okay. Okay. So the first problem here is asking, we have seen methods to convert haloalkanes into alcohols. Provide the information requested in the boxes below. So we have this molecule here in the reactant, and we have to choose which reagent would be the best reagent to create this alcohol over here and this alkene over here,
Hmm.
right? So the reagents that we have here is going to be water, H2O, which is neutral. There's no formal charge attached to it, right?
Hmm.
That means that it is stable. It's happy, right? So because it's stable and happy, it's not going to be reactive. It's not a strong nucleophile,
Hmm.
okay? When you see NaOH right here, sodium is going to be positively charged, and whatever is attached to the sodium is going to be negatively charged. So the negative charge here is the OH,
Would that
right?
make it polar?
That would make it polar because of the charge right there.
Yes.
Yep.
Yes.
And this full negative charge right here, right, is going to be very reactive. Like it's unstable because molecules do not want to have charges um at all because that makes it reactive, able to be neutral to be stable, right?
Hmm.
And then this HOOH here is a peroxide, which is also neutral. And this bond right here between the two oxygens is called a peroxide bond, but that's not going to be used for this reaction here, right? That's going to do a different reaction for like alkenes, but this one here we're not worried about.
Hmm.
Okay, okay. So this neutral water molecule here and this hydroxide ion here is going to be very similar, right? But different. This is the deep protein version of the water right here. Okay.
Hmm.
And now we're trying to substitute this bromine here with this OH right here, right? For this reaction.
Hmm.
And to do that, we need a strong nucleophile. Are you familiar with the term nucleophile?
Uh, no, not I would like for you to explain. I kind of was
Hmm.
watching Chad's prep, but I wouldn't say I'm strong with
Hmm.
that.
Okay. Yeah. So uh let's go over the difference between nucleophile and electrophile. So nucleophile is going to be nucleus loving, right? Where nucleo is going to be the nucleus, phile is going to be loving. And in Gen Chem, do you remember the nucleus of an atom? What are they composed of? Like subatomic particles? Like are they going to
Hmm.
be composed of electrons, protons, neutrons,
Hmm.
in the nucleus of the atoms?
Hmm.
Mhm. The nucleus is going to have protons and neutrons, right?
Hmm.
And the charge of a proton is positively charged.
Hmm.
So a nucleophile is going to love positive charges, and opposite charges will attract. So nucleophiles to attract positive charges, they're going to be partial negative charge or fully negative charge, right? This symbol here, negative, is like showing a partial negative charge, or this negative sign here is going to show a full negative charge, right?
Hmm.
That negative charge here is going to attract a positive charge.
Hmm.
Okay. Now let's go over electrophile. Electrophile is going to be electron loving. Okay. So that means that electrons are going to be negatively charged. So to attract negative charges, the electrophile is going to be partial positive charge or fully positive charge, like that.
Hmm.
Okay. Okay. So now in the OChem, right?
Hmm.
A lot of reactions would be like this. Nucleophiles will attack electrophiles. right? And what that means is that the negative charge here, right? The negative charge of the nucleophile is going to go towards the positive charge. So let's say the nucleophile, like we said, is negatively charged and the electrophiles are positively charged, right? The negative charge is going to attack the positive charge, meaning that it's trying to make a bond. It's trying to make a bond with the electrophile right there,
Mm-hmm.
right? Okay. Um, Now that's because the nucleophiles with the negative charge is going to have a pair of electrons like that, or it's gonna come from a bond, right? From the pair of electrons, and it's gonna attack something that's missing electrons, that has a void of electrons right there.
Yes. Mm-hmm.
Okay. 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 So now, if we go back to over here, this carbon here, do you know the partial charge of that carbon right there? Like, is it partial positive or partial negative?
It
Based
would
on
be
what?
partial positive, right?
Yep, partial positive because it's attached to this electronegative bromine atom that's gonna pull or withdraw electrons from the carbon. And because this carbon here is losing electrons, losing negative charge, this carbon here is gonna become positively charged. Right? And because it's partial positive charge, would this be the nucleophile or electrophile?
I'm sorry, can you repeat that last part?
Yeah. Um, because this carbon here is partial positive charge, is it going to be a nucleophile or electrophile?
No, if that's positive, wouldn't it? It would be an electrophile, right?
Yep, it would be an electrophile, right? Because electrophiles are going to be positive charge, nucleophiles are going to be negatively charged,
Mm-hmm.
right? Okay. Now, um, which one looks like the stronger nucleophile to you, right? The partial negative charge oxygen on the water here, or the full negative charge oxygen here?
Mm, okay. Um, wouldn't it prefer the partial one?
So, the partial one is more stable, right? Like we said, it's like neutral and more stable, less reactive, right? But the full negative charge oxygen here is less stable,
Mm-hmm.
right?
Mm-hmm.
And because it's less stable, it's more reactive. It's a stronger nucleophile.
So we don't want that.
Yeah. So in this
Or-
case, we do want that
Okay,
because we wanted a reaction to happen. If we do not want a reaction to happen, then we want water,
got it. Yeah, that's
right?
because that's neutral. Yeah, yeah.
Yes, neutral, right. But
Mm-hmm.
because we want a reaction to happen and substitute this bromine and substitute it with the OH here, we want a very reactive, unstable reagent, which is this hydroxide ion here. A strong
Mm-hmm.
nucleophile, right? This is a strong nucleophile here.
Mm-hmm.
Okay. Now, this strong nucleophile here has three pairs of electrons specifically. Right? This oxygen here has three pairs of electrons. It's going to use one of its pairs of electrons to attack this partial positive carbon right here,
Mm-hmm.
right? And that's going to make a bond. That's trying to make a bond with that carbon right there.
Isn't that like a backside attack or
Yep,
something?
this is going to be backside attack, right? SN2. Because what that means is that it's going to go on the backside of where this good leaving group is, right? This
And
bromine here is
that's
a good leaving
kicking that
group.
out. It's gonna
Yep,
be
it's
like,
going to kick it out, correct. And when that kicks it out, we're going to get this here, where we substitute the bromine with the OH right there, right? That's good. And that's going to be an SN2 reaction. You got that.
mm-hmm.
And notice how this electrophile here, carbon, we're going to call that the substrate. Okay. For SN2 reactions, SN2 reactions need a lot of space to attack. Because you know how you said this is a backside attack right here?
Mm-hmm. Mm-hmm.
There needs to be space to attack that.
Yeah.
If there is like so many groups around it, like let's say there's a methyl group there, ethyl group here, it's so bulky, right? It's like so crowded around that electrophile, around that substrate. That's
Mm-hmm.
what we call steric hindrance,
Mm-hmm.
right? And SN2 reactions would not work well with steric hindrance. This substrate here specifically is bonded to only one other carbon, right? So we call that a primary substrate.
Mm-hmm.
Right. I'll make it more clear here. Like this is
Yeah.
let's say this is the leaving group right here, and then let's say
Mm-hmm.
this is leaving group there,
Mm-hmm.
and then let's say this is the leaving group here, and then these carbons here that I'm gonna color code in red are the substrate carbons or the
Yes.
electrophiles because they're partial positive charge.
Yes.
Um, this one right here is primary substrate because this substrate
Connected to
here
one.
attached to one carbon. This is secondary. This is tertiary.
Got it. Okay, I see.
Hmm.
Mm-hmm.
Right. This is secondary because it's attached to two other carbons. This is tertiary because it's attached to three other carbons right there. Right.
Perfect. I see.
And then, like we said, SN2 reactions would work. well with primary or secondary substrates, right?
Yes.
More well with primary because there's more space for the nucleophile to attack that electrophile right there. It does not work well with tertiary carbons because there's so much space here. It's so crowded,
Yes.
so bulky, right? Okay. Now the alkene product, which is a carbon double bond carbon, will always come from an elimination reaction, either an E2 reaction or E1 reaction. So whenever you see an alkene, always think of an E reaction, E2 or E1.
And
Okay.
how am I able to identify like the alkenes? See, that's why I'm confused on.
Like for the product, like in this case, it's
Mm-hmm.
specifically given to you, right?
Mm-hmm.
Where the alkene is gonna be a carbon double bonded to another carbon. That's the alkene right there,
Got
right?
it. Okay, I see.
We see over here there's no alkene because we don't see any double bonds,
Got it.
right? But in this example here, we specifically see double bond here between these two carbon atoms.
Got it.
Okay.
Okay, I see.
hmm
Mhm.
Yep. Okay. Okay. Now I'm gonna show you the mechanism of that here because when you see this reaction right here, we're either gonna do E2 or E1 reaction.
Mhm.
And let's talk about E1 first. E1 is always gonna go with SN1. They always happen together. SN1 and E1 reactions. Okay? And let me make it more clear here. SN1, E1 reactions always happen together. And a very important part about this reaction is that they are going to go through a carbocation intermediate. Are you familiar with that? Have you heard about that term, carbocation?
Uh, a little bit, but I thought that was more in Gen Chem or no?
Uh-huh.
Mm.
Right. So carbocation right here is going to be a carbon that is positively charged because cation means positive charge, right? Anion means negative charge. Okay, so if I have something like this where um we have this structure and this carbon here has a positive charge on top of it, that is going to be the carbocation because this carbon here has a positive charge. Right, that's a carbocation. And
Yep.
specifically, how many carbons is this carbon attached to here? How many other carbons is that carbon attached to?
Two.
Two, right. So we're going to call this a secondary carbocation, right? This
Got
right
it.
here is a primary carbocation.
Mm-hmm.
This right here is a tertiary carbocation. Okay.
Perfect.
And when we talk about the stability, like how stable these carbocations are to each other, stability will increase from left to right.
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 Ah. Mm-hmm.
hmm And think of it like this. When you see a positive charge on a carbon, that means that it's missing electrons, right? Because you know
Mm-hmm.
electrons are negatively charged.
Mm-hmm.
And because it's missing electrons, um, and it's positive charge, it's gonna want to gain electrons to be neutral again. Because you know how we said earlier, neutral molecules are happy and stable.
Mm-hmm.
Think of the R groups, which are the carbon, hydrocarbon chains around it, as friends who are gonna donate electrons naturally, inductively to the positive charge, right? So this arrow here shows electron donation by induction, right? And these here are R groups. It could be anything. It could be a methyl group. It could be an isopropyl group. It could be an ethyl group. It could be a propyl group, like any hydrocarbon chain, right? If there's more hydrocarbon chains substituting or like around the carbocation, they're gonna donate electrons to the carbocation, making it more stable, right?
Got it.
If we look at the secondary carbocation over here, there's only two R groups, so there's only two friends donating electrons to this carbon here who's missing electrons.
Mm-hmm.
Right. Whereas the primary carbocation here only has one R group, um, donating electrons to that carbocation right there. Right. So that's why this carbocation here is the most stable because it's gaining a lot of electrons from its friends, its R groups, its surroundings, like that.
Got
Okay.
it.
Yep. And then that right there is called hyperconjugation. Right. hyperconjugation. Okay. Now, let me show you the mechanism for SN1 E1 really quick. If I have this,
Really quick,
yeah,
sorry.
uh-huh.
So the friend's donating it to the carbon cation, right?
Yeah, carbocation.
Yes.
Uh-huh.
So is that's the thing called hyperconjugation, right?
Yeah, that's the hyperconjugation right there. The
Donating electrons
donation of electrons inductively, right?
inductively. Okay, perfect.
Yeah. hmm Because the reason that's happening is because these groups here, you know how these are bonds,
Mm-hmm.
right? Um, how many electrons are in a bond?
Two. Mm-hmm.
Two electrons in a bond. So there's just more electrons around the carbocation, and those electrons that are in the bond are gonna stabilize or make the positive charge more neutral, right?
Mm-hmm.
Whereas like if there's only like le a little bit of electrons around, the positive charge is not gonna be neutralized or
Mm-hmm.
stabilized as
Of course.
much.
Mm-hmm.
Yeah.
Perfect.
hmm Okay. So now, once we have this haloalkane right here, haloalkane meaning we have a halogen like chlorine, bromine, iodine. Alkane meaning like any carbons and hydrogen group like that, right?
Mm-hmm.
Um, what kind of substrate is this here? Like we know this is the good leaving group, but is this a primary, secondary, or tertiary substrate?
It would be tertiary, right?
It looks tertiary,
But it's
right?
actually secondary,
It's
huh?
actually secondary because we look at
It's
how
only
many carbons it's attached to, right?
okay.
It's attached to two carbons. This is not carbon, so we don't count that. Like I also made the same mistake.
Okay,
Yeah.
got it. I see.
Right. Yeah. Don't worry because when I first learned about primary, secondary, tertiary, I also thought this was tertiary because there's like I saw three groups coming out, right?
Yeah.
But it's not attached to like three carbons. It's only attached to two carbons. That's the most important part right there,
Mhm.
right? Okay. Um. Now for SN1E1 mechanism, right? We do not want to form a primary or methyl, and I'll tell you what that is, carbocation. I'm going to abbreviate carbocation as that C plus right there, right? We don't want that because that's too unstable to exist, right?
Mhm.
So I already showed you a methyl carbocation, I mean primary carbocation, which is this right here.
Mhm.
A methyl carbocation is even less stable because it has no friends at all. It has no
Mhm.
um no R groups around it. So
Mhm.
let's say we have a carbon right there with a positive charge. It's
Mhm.
attached to three hydrogen atoms. No R
Mhm.
groups,
Yeah.
right? And hydrogen atoms here like is not strong enough to donate electrons,
Yeah.
right? Like this primary carbocation here has two hydrogens. This secondary carbocation here has uh one hydrogen. And this tertiary carbocation here has zero hydrogens, right? Before, you know how we said neutral carbons have four bonds? Like if we have something like this carbon here would have two hydrogens if it's neutral. Carbocations would only have three bonds, right? So I take that back. Um, like this carbon here and the carbocation here, how many hydrogens would it have if it has three bonds?
In total,
hmm
it would have. Mm, can I see it or?
hmm Yeah. So you know how we have a carbon with a positive charge here? How
Mhm.
many bonds would that carbon have if it's positively charged?
One.
We see only one bond right here, right?
There's.
But a positive charge carbon, we have three bonds. Three bonds.
Can you explain that again really quick?
Yeah, uh-huh. So let me explain to you the form of charge, right? If you look on the periodic table, carbon is going to be on the group 4A. Carbon is going to
Mhm.
be right there, right? That means carbon wants to have four electrons to itself
Got it.
in a bond to be neutral, right? So if I show you, let's say, a methane group like this, you said that each bond here represents two electrons, right? Two electrons
Mhm.
here, two electrons here, two electrons here, two electrons here.
Mhm.
Um, when we calculate from our charge over here, let's calculate from a charge of this carbon here, like if it's going to be positive charge, neutral, or negative charge. Okay, so
Mhm.
to do that, we look at what group it's on. It's on group 4, so it wants four electrons to itself.
Mhm.
Let's look at this bond over here. One
Mhm.
bond belongs to the carbon. I mean, one electron belongs to the carbon. The other
Mhm.
electron belongs to the carbon right there. The hydrogen right there.
Mhm.
Right. So this carbon here will have one, two,
Mhm.
three,
Mhm.
four,
Mhm.
four electrons to itself. So 4 minus 4 is
Zero.
0. So that carbon there is going to be neutral. Neutral. Formal charge of 0. No positive charge, no negative charge. Okay?
Got it.
But now let's look at this carbon over here. What is the formal charge of this carbon over here?
Let me see. Give me 1 second. 1, 2, 3. It would be 4 plus 3 is it would be positive one, right?
Yeah, it would be positive because carbon is on the fourth group.
Fourth,
It
yeah.
wants 4 electrons, but it has
It's 3.
three
Mm-hmm.
electrons. 4 minus 3
Mm-hmm.
is plus 1.
Mm-hmm.
So this carbon here will have a positive charge. And this is what we call a carbocation, like that. Okay.
Got it. Perfect.
Now, let me give you one more here. Find the formal charge of this carbon here.
I have a quick, or actually, hold up, I'll do it myself.
Hmm
I'm just kind of here. I'll do it really quick, and then I'll tell.
hmm
Would it be -1?
Negative charge because carbon is on the fourth group, so it was 4 electrons, but it has one, two, three, and this pair of electrons here belongs to carbon itself. It doesn't belong to anyone else, it belongs to the carbon. So that's one, two, three, four, 5 electrons. 4 minus 5 is -1. So this carbon here will be a negative charge. And this is what we call a carb anion.
And
hmm Anion because it's negative charge.
it's
Okay. Now, if we go back over here and we look at this carbocation over here,
mm-hmm.
right? How many electrons do you think it has right now if it has a positive charge?
Would have
Like,
like 1.
uh-huh. How many carbons does carbon want based on the periodic table? What group is it on?
Oh, 4.
4, right? 4.
Yeah.
Uh-huh. And then
If it owns
4,
1, it would just be 3, right?
yeah, it would just be 3.
Yeah.
But we only see one over here, right?
Yeah.
We only see one over here. So that
Mm-hmm.
means there's two invisible ones that we do not see.
Mm-hmm.
And those two invisible ones that we do not see are the hydrogens. Right? Because when
Mm-hmm.
you see a bond line form, hydrogens
Hmm.
are implied, like
Got
they're
it.
invisible, right?
Hmm.
So a lot of people would think that this carbon here with the carbocation would be
Hmm.
attached to 3 hydrogens, but that's not
Yes.
right, right? Because
I'm
if
going
it's
to touch
attached
it
to three
too.
hydrogens, this carbon would not be positive charge at all,
Yeah, no,
right?
you're
It would be neutral,
right. Yeah, you're right.
right? How many hydrogen atoms is this carbon attached to here? How
4.
many? Four. So, how many bonds do you see right now attached
I
to this
see 2
carbon?
bonds,
Uh-huh.
so it would be 2, right?
2 hydrogens. So if it's 2 hydrogens right
2
there,
hydrogens.
then that would make this carbon neutral.
Oh, okay.
Neutral, right. Uh-huh. But this carbon here is positive charge, so only wants 3 bonds. It already has
Mhm.
2. We don't see one,
Yeah.
right? So that's one bond to hydrogen right there. Okay. Um,
Oh, okay.
but
Got
if
it.
you look at this carbon over here, then that carbon will have 2 hydrogens,
Hmm.
right? Because this carbon here is neutral. It's not positive charge.
So that has 3 hydrogens from what you showed me.
This carbon here will have 2 hydrogens.
Oh no, the first one.
The first one, yes, the first one right here. One, two, three. Yeah,
Yeah. Okay,
that would
perfect.
have 3 hydrogens, correct.
That would have 2. Okay.
hmm Now this one over here, how many hydrogen atoms would it have if it's positive charge?
1, 2, 3. I'm either saying 3 or 2.
So, for a positive charge carbon, how many bonds would that carbon have to be positively charged?
It would need to have 3.
Uh-huh, 3 bonds. How many bonds do you see right now?
3.
3. So that means it will have 0
Oh, oh, you're
hydrogen
subtracting.
bonds.
Okay, I'm over here
Uh-huh,
thinking you're adding. You're like kind of
uh-huh.
subtracting it from.
No, yeah, you're subtracting.
Okay,
Uh-huh.
okay, yes,
Yeah,
yes.
uh-huh.
Mhm.
Yeah. Okay. So it's like 3 minus 2 here, 1 hydrogen.
Yes,
3
one
minus 1
hydrogens.
here,
Yeah,
2 hydrogens. Yeah.
you might.
Mm-hmm.
Okay, got it.
Yeah.
Hmm.
Yeah. Okay. So now if we go back over here
Hmm.
and if we use a weak base, weak nucleophile, right? And there's only three that you need to know. Those are the neutral ones: water, H2O, alcohol, ROH, and carboxylic acid, right? But more commonly, you're gonna see these two here: water or alcohol, ROH, right?
Mm-hmm.
R here could be anything. It could be ethyl group like that. It could be an isopropyl group like that. It could be a terbutyl group like that, or it could be a propyl group like that, right? That R group is random. This is R, R, R. Like it's a variable hydrocarbon chain,
Mm-hmm.
right? But these are alcohols over here. Okay. Whenever you see that, always think that you could do an SN1 or E1 reaction. So for example, let's use ethanol, right, which is an alcohol. Okay.
Mm-hmm.
Now the mechanism here for SN1 is going to do salicylisis. So that's just part of the study guide right here, salicylisis. I'm going to draw out this more clearly to you and explain to you the mechanism. What is the partial charge of this hydrogen here?
The partial charge of this hydrogen. I would have to go back on the periodic table, huh?
hmm And you can also look at what is attached to, like this atom here. Like, is
Oxygen.
it more or less electronegative? Uh-huh. Right.
Um, but isn't like hydrogen like one charge?
hmm So hydrogen here is attached to oxygen, which oxygen is more electronegative than hydrogen, right? So if it's more electronegative than oxygen than hydrogen, what is this oxygen gonna do? Is it gonna pull electrons from hydrogen, or is the hydrogen gonna pull electrons from oxygen? Which
It's
one
gonna,
has a stronger pull?
well, the oxygen has a stronger pull.
Yep. Uh-huh. Yep. So oxygen is gonna pull electrons from the hydrogen, and what does that say about the partial charge when oxygen is pulling electrons from the hydrogen? What does it say about the partial charge of oxygen and hydrogen?
That it's stronger.
Uh-huh. Yeah, so oxygen is stronger than hydrogen, right?
hmm
And because it's stronger than hydrogen, it's gonna pull like the electrons of this bond with the two electrons here towards the oxygen here. What charge is an electron? Positive or negative?
Oh, positive.
So electrons are gonna be negatively charged electrons.
Oh, electrons.
Uh-huh.
Yeah, but they
Yeah.
love positive,
Yeah,
right?
they love positive charge, right? They love positive charge because opposite charges attract, but electrons themselves are negative charge. So because this oxygen here is like pulling
Mm,
electrons
yeah,
in, is it going to be more negative charge or less negative charge if it's pulling more electrons in?
less negative charged.
Oh, so you know how we said electrons are negatively charged?
Yeah.
Yeah. When this oxygen here is pulling more electrons, it's pulling in more negative charge.
Uh-huh.
So it's going to be more negatively charged.
Mm. Okay, that's why I'm confused because I
Uh,
thought that they love partial positive. That's why I'm saying positive.
Yeah, so they love positive charge, but I'm asking like what charge they are, not what charge they love.
Got it. Okay, okay. So,
Uh-huh. Yeah. So this oxygen here is partial negative charge
hmm
because it's more electronegative than hydrogen, so it's gonna pull electrons towards itself. And because it's partial negative charge, it's gonna be a nucleophile that loves positive charge, so it's gonna attack an electrophile.
Perfect.
Right. This hydrogen here is partial positive charge because it's losing electrons, losing negative charge. Right.
hmm hmm
So if we have a lot of this around, what partial charge does this bromine have here? Partial with negative or partial positive?
Partial negative.
Yep, partial negative because it's more electronegative than the carbon here.
hmm
So that's gonna pull on the carbon's electrons, making the bromine partial negative and the carbon partial positive,
hmm
right? And the hydrogens of the alcohol are gonna surround the bromine, right? These hydrogens here that I'm drawing around the bromine, right, are gonna be the hydrogens of the alcohol right here, right?
hmm
I didn't draw out the other parts, but those hydrogens here are the partial positive hydrogens that are going to surround the partial negative bromine because opposite charges attract, right?
hmm
And this Savolysis here, when it's wrapped around, it's going to grab the bromine away and kick it out, the molecule. So the bromine is going to leave the molecule with the hydrogens around it,
hmm
okay? Now, when that happens right there, this carbon here lost a bond, right? Because the bromine there is no longer there. So because it lost the bond, what charge would this carbon have here?
A positive.
A positive charge. And we call that a carbocation, right? A
Mm-hmm.
carbon with a positive charge. What kind of carbocation is it? Primary, secondary, or tertiary?
It's secondary.
Secondary carbocation. So that's good enough to exist. So we can keep going with the mechanism here.
As long
And
as it's not tertiary, right?
tertiary is even more stable.
Oh yeah. Oh gosh.
Yeah.
Yes. Okay.
Uh-huh.
Primary isn't because it's not.
Uh-huh.
It doesn't have much
Yeah.
donators. Got it.
Yeah, right. But we don't want primary. We don't want
Yeah.
primary at all.
No.
Yeah. hmm
Okay. Got it.
Like for example, if we have let's say this molecule over here with a primary substrate because this carbon is attached to one other carbon,
Mm-hmm.
and we react it with water, which is one of the weak base weak nucleophiles, right?
Mm-hmm.
We know that the water hydrogen here is going to surround the positive charge the negative charge bromine, right? And kick it
Mm-hmm.
out. And when we try to do that, what kind of carbocation do we form here?
Mm-hmm. Primary.
Yeah, primary, because this carbon here is attached to one other carbon, right? Is this
Mm-hmm.
stable? Is this
No, it's
primary?
not stable.
Yeah, no, it's not stable. So this right here would not work. No reaction,
Got it. Okay.
right? NR no reaction because that is an unstable intermediate. It cannot form.
Got it. Okay.
Okay, but this one here is able to form because it is secondary, more stable than the primary.
Mm-hmm.
Okay, now what is this here? A nucleophile or an electrophile?
That is going to be an electrophile.
Yeah, because it's positively charged.
Mm-hmm.
Correct. Now, if we do SN1 over here, let's bring in another like equivalent of this alcohol here because we have a lot of them.
Mm-hmm.
What atom here is going to be the negative charge, the partial negative charge? Is it this carbon, this oxygen, or this hydrogen here? What atom is the partial negative charge?
It would be the oxygen, right?
Yeah, the oxygen will be partial negative charge. It has two pairs of electrons, but we only need one,
Mm-hmm.
right? That oxygen there that's partial negative charge is the nucleophile. And
Mm-hmm.
what attacks what? Does the nucleophile attack the electrophile, or does the electrophile attack the nucleophile?
Electrophile technical.
Oh, so in this case
Oh
right here,
wait.
this is a common mistake. Nucleophiles will attack electrophiles, right?
Ah, yes.
Right.
No. Okay, you're right.
Because we're trying to make a bond here. There's nothing for this electrophile to use to make a bond with that atom right there.
Mm-hmm.
Right. But the nucleophile here, you know how it has a pair of electrons right there, those two electrons?
Mm-hmm.
That nucleophile there can use those two electrons to attack that electrophile right there, to make a bond with that electrophile right there, like that.
Mm. Okay.
Okay? Right? Now let's calculate the formal charge of this hydrogen here because this is gonna be very helpful to like describe like how we've calculated formal charge in the next step. So oxygen on the periodic table is gonna be on the sixth group, sixth column.
Mm-hmm.
Right. So what is the formal charge of this oxygen here? How did we calculate formal charge again for this
Okay. So I'm
oxygen?
gonna Jane 6, and then if it's at 1. I have a question.
Mm-hmm.
It doesn't need to form a full octet, or is it just that specific? Like,
Yeah. So don't think about full octet here. Think about
okay,
formal charge here.
okay,
Yeah.
okay. One, two.
So because it's on the sixth group, it wants six electrons to itself. Just count how many electrons this oxygen has to itself.
Would it have four to itself?
It would have four to itself from the lone electrons, right? One, two, three,
Hmm.
four. But this
Oh,
bond
yes,
here,
yes, yes,
yeah.
yes. One, two, three, 4, 5, 6. It would be neutral, no?
Yeah, six. It has six electrons to itself. Six
Hmm.
minus six is zero,
Hmm.
which is neutral. So that's
Hmm.
correct. This is neutral. The reason why I made you do that is because in some reactions, right, they don't give you the pair of electrons at all. It's invisible,
Yes.
right? So but you gotta know like how many pairs of electrons it has based on its charge. So you know
Hmm.
how there's no charge given as oxygen over here? Like we don't see a plus sign or we don't see a negative sign. It's just
Hmm.
neutral, right?
Hmm.
Because it's neutral, we know how many electrons does oxygen have to itself right now if it's neutral.
Hmm.
Like how many? How many electrons does oxygen have to itself if it's
Four.
neutral? Uh-huh.
4.
Four. So
Six.
what
6, right?
six? Yeah,
Yes,
six. Right, right, right.
right,
Uh-huh.
right.
Uh-huh. Because it's on the sixth group.
Yeah, 6 group, yeah.
So, but how many do we see now? Like we only see one,
One,
and there's a bond right here between
the
the O and
bond,
H.
but we don't see the other
Two.
4.
Yeah, we don't see the other four. Those other four are invisible,
Hmm.
invisible lone
Hmm.
electrons like that, right?
Hmm.
But because there's four invisible lone electrons, we there's two pairs of those electrons,
Mm-hmm.
right? Okay. So I'm gonna draw out the pairs here that are invisible. We only need one of them, which is the nucleophile here.
Mm-hmm.
That's gonna be the nucleophile that will attack this electrophile right there, like that.
Got
Okay.
it.
Now, when that happens, this is what happens as a result. So this blue carbon here, right, that I dotted right there,
Mm-hmm.
is gonna make a new like this right here is a new bond, new, right? Bond between that carbon and oxygen right here, right?
Mm-hmm.
And I'm gonna highlight that new bond in yellow right there, like this, right? You know how there's two electrons in here?
Mm-hmm.
That new bond, those two electrons in the new bond came from this pair of electrons right here in yellow, right
Mm-hmm.
there,
Mm-hmm.
right? So now oxygen here, it's still attached to an ethyl group, like whatever that R group is, right? So
Mm-hmm.
I'm gonna draw the ethyl group out like that. It's still attached to a hydrogen, and it has one more pair of electrons that we didn't use, which is down
Yeah.
here, right?
So are you gonna add those on top? Or
Yeah, add those on top like that, correct. Now calculate the formal charge of this oxygen over here.
okay, it's connected to one, two, three, four, five. It would be one, right?
Yeah, one, which
Mm-hmm.
is gonna be a positive charge. So this oxygen here is gonna be positively charged like that,
Got
right?
it. Okay.
But our product, we don't want it to be positive charge or negative charge because that's not stable,
Yeah.
right? We want to make it neutral, so we want
Got
to stabilize this right here.
it.
To make
Yes.
this oxygen neutral right here, um, we want to have it, we want to make it so that it has six electrons to itself, right? To make it neutral, zero
Mm-hmm.
charge.
Mm-hmm.
So to do that, you know how that it's attached to a hydrogen? That's a proton right there. We could deprotonate it. We could get rid of this hydrogen right here and like this two electrons right here can go onto that oxygen to make it neutral, right? Like if the hydrogen is no longer
Mm-hmm.
there and the two electrons of this bond right here are onto that oxygen, it will have
Mm-hmm.
one, two, three, four, five, six electrons. So that's neutral, right?
Mm-hmm.
And to do that, this right here is going to be very acidic because of that, right? It wants to go away now to make this oxygen neutral, right?
Mm-hmm.
So a base that can grab that acid is another alcohol, like because we have a lot of those around, right? So this oxygen here, with you know how it has two pairs of electrons,
Mm-hmm.
it could either act as a nucleophile or it could act as a base, right? In the first reaction that I showed you over here, it acted as a nucleophile. This alcohol here is a nucleophile because it's attacking an electrophile to make a new bond between an
Mm-hmm.
electrophile and a nucleophile. Because whenever a nucleophile attacks an electrophile, we always create a new bond between the nucleophile and the electrophile like that,
Mm-hmm.
right? But now in the next step here, we're not going to do a nucleophile electrophile reaction. We're going to do a acid base reaction, right? Where this oxygen here is going to be the base that's going to use one of its pairs of electrons to grab that hydrogen right there. Does that make sense of what on like why this partial negative charge oxygen here is going to grab that hydrogen right there,
Mm-hmm.
right? And when this hydrogen is being grabbed, it's going to be taken away from this oxygen right here. So the electrons on this bond right here are going to break off and
And
go
break
onto the
off.
oxygen right there,
Mm-hmm. Yes.
right? And then when that happens, we're going to get this molecule over here where because we already have one pair of electrons, which is this right here. It's gonna gain another pair of electrons, which I could highlight in pink, let's say, right? That pink bond right there that represents two electrons are gonna be this pair of electrons here in pink, like that, right?
Mm-hmm.
That's neo right there. That pink pair of electrons came from this bond right here, like that. Okay, and now it's neutral because it has six electrons to itself. One, two, three, four, five, six, like that.
Got it. Okay.
Okay.
No, it's neutral. Okay.
Uh-huh. And this is SN1. This is the SN1 product right there, like that.
SN1.
hmm Okay. And you know how we said earlier, SN1 always happens with E1?
Mm-hmm.
Uh, let me summarize this right here for you and then move on to E1. So the first step of all SN1 and E1 mechanism is that the leaving group leaves first, right? And we know that it's able to leave because of this product solvent here that with the weak base weak nucleophile, which is either going to be water, alcohol, or carboxylic acid. And when it leaves first, we form a carbocation, which is the electrophile, right?
Mm-hmm.
And then from here, we could do SN1 or E1. We chose to do SN1, where we use the nucleophile to attack the
Mm-hmm.
electrophile, have this intermediate where we deprotonated it to make it neutral and stable.
Mm-hmm.
Okay, now let's do E1 here. For E1, right? Let's use the same molecule, same halocane right here,
Mm-hmm.
and then we do E1 with, let's say, ethanol, the same set of reagents, same set of reactants. Okay, what's the very first step? The very first step of SN1 and E1.
to get to the leaving group.
Yep. Let's kick out the leaving group first. To form what intermediate? What is the name of the intermediate?
The intermediate is the isn't that hyperconjugation? No, wait.
Oh, so that's a factor that describes why the carbocation is
Oh,
stable. So the intermediate here is carbocation.
carbocation.
That gets formed because this right here it gets formed after the leaving group leaves, and that right there is a carbocation. Right, this
Carbo.
one specifically is a carbocation.
Let's see.
hmm Right now, once I have this carbocation intermediate, and we want to do E1, right? This is gonna be a little bit more tricky because for E reactions, you know how we said we're gonna form a double bond.
Mm-hmm.
We're either gonna form a double bond like here, right? Or we're gonna form a double bond here.
Mm-hmm.
Okay. The double bond is gonna be like attached to the carbon with a positive charge. Are you familiar with alkene stability, like double bond stability?
Mm-mm.
So, let's go over that. I'm just gonna draw out you different double bonds right here.
Mm-hmm.
Okay. What is the difference you see between all of these double bonds here? Like, what is the thing that makes these double bonds different?
What? How much bonds are connected to?
Uh-huh. Yeah. How much bonds are connected to? The more bonds that the alkene is connected to, the more stable it's gonna be. And it's very similar to the carbocation stability. Think of it as like the more friends it has, the more stable it's gonna be.
To the more
hmm
stable.
Right.
And then what is this called again? The
So this one right here, you could also say that this is gonna be hyperconjugation.
okay.
Yeah. Just like the carbocation. Okay. Well, this one here is talk about alkene stability. We're gonna compare we're gonna compare um how stable different alkenes are.
Mm-hmm.
Okay. Um, Now this right here is the most stable alkene because it has the most groups around it, most bonds around attached to it. This right here would be the least stable because it is bonded to four hydrogens, right? But they're invisible. Those hydrogens are not going to do anything to the alkene. They're not going to like donate electrons or like
Mm-hmm.
support the alkene, right? Okay. Um, Now let's categorize this. This right here is an unsubstituted, right?
Mm-hmm.
Unsubstituted alkene because there's no group attached to it. This is a mono substituted alkene because there's one group attached to it. And then these three here are the di substituted alkene because there's two groups attached to it,
Mm-hmm.
right? This right here is a tri substituted alkene. This right here is a tetra substituted alkene. Okay. Now for the di substituted alkene, we could break that down even further. This is a trans alkene, right? This is a cis alkene, and this is a geminal alkene. Right. Trans meaning that if you make a line through the alkene right there, the two groups of the alkene are opposite from each other, different from each other. Cis meaning same, is that if you make a line through the double bond, the two groups are on the same side of the line, right? You could
Mm-hmm.
either be on side A or side B here because the two groups are on the same side. That's cis. You could be a side A or side B here because the two groups are on the opposite sides. One is side A, one side B. They're opposite from each other, like that.
Mm-hmm.
Right. Okay. Geminal is gonna be the that we have two groups on the same carbon, right? You know how these two groups here are coming off of the same carbon?
Mm-hmm.
That's geminal right there. Now, geminal and cis alkene are gonna be similar in stability. Like they're gonna be very similar, right? But everything is gonna be like this in terms of stability. Now, the reason why the trans alkene is more stable than the cis alkene is because you know how the two argues are like facing away from each other? They're like far
Yeah.
away from each other. They're not gonna touch each other. They're not gonna bump into each other. But you know how the two argues here on the cis alkene are like very close. They're gonna touch each other. They're gonna into each other.
Mm-hmm.
That's steric hindrance right there. That increases steric hindrance. And we don't want steric hindrance. Molecules with steric hindrance are less stable.
Mm-hmm.
Right. Same with the geminal alkene. The two argues are gonna have steric hindrance as well.
Mm-hmm.
Okay. Okay, so now if we go back over here, like we said earlier, you know how I said I could form, let's say this is alkene A or this is alkene B. Which alkene do you want to form to be more stable, to form the more stable major product?
I would say, let me think.
hmm Which one is more substituted? I could make it more clear for you by drawing out the different possible. products here. You could
Mhm.
form that. You could form this. Another possible product that you could form is going to be this right here.
I would say honestly, I would do the last one, the third one.
Uh-huh. So the third one right here. How many groups is attached to this alkene here? How many groups?
Mm, none.
Uh-huh.
Okay,
One.
I see.
Uh-huh. One group
So
right there.
I would say then it would be the f for the first one or the second one.
Because they're both di
They're both yeah, you're right. You're
substituted.
right.
Mm-hmm.
Okay.
But they're different di substituted ones because you know how there's three different
The
di?
yeah,
Uh-huh.
there's
So,
Gemini or cis, and for the second one cis, the first one's
mhm.
Gemini. Not Gemini. That one's like, wouldn't it be trans?
Trans, right? Because they're on opposite sides of the line.
Yeah,
One is over here, another one's over here. And which one is more stable, trans or cis?
cis.
So if we look at this over here, if we look at the cis one, these two groups here are so close to each other. Do we like that, steric hindrance?
No, actually, no,
No,
no.
right. It's trans because the two groups here are opposite from each other. So trans right here is going
Trans.
to be more stable than cis, right? Because
Ah,
of less steric hindrance.
got it. Okay,
hmm So this is the major product that we're going to form right here for E1.
got it.
Okay.
Okay, okay.
So to form that major product right there,
Hmm.
we're gonna call the first carbon attached to the carbocation, right? Like you know how this is the carbocation right here, the carbon with
Hmm.
the positive charge. That first carbon right there is gonna be the alpha carbon, right? The second carbon away from it is the beta carbon,
Hmm.
right? And to do the E1 reaction, we're interested in the beta proton, the beta hydrogens, right? So we have one beta hydrogen here, or like we have two here and three here, but we're only interested in one of them, right? Like this beta hydrogen has two beta hydrogens. This beta carbon here, I mean, this beta carbon has two beta hydrogens. This
Hmm.
beta carbon has three beta hydrogens, but we're not interested in all of them. We're only interested in one of them for the
Yes,
mechanism, okay?
yes.
And like we said earlier, we're interested in the one that would create this alkene here. So which one do you think that would be? A or B that would create this alkene here? Which one is closer to this alkene here? A or B?
Mm. Honestly, I want to say A,
hmm A,
but I
yeah,
feel like
right?
it's B.
It is A. It is A.
Is it?
Right.
Okay.
It is because you know how this carbon here is the carbocation right here, and you know
Mm-hmm.
how we want to form the like a double bond right here, an alkene right here,
Mm-hmm.
right? Um, that right there is gonna be closer to A, like that.
But how if those are closer together to the other one? Can
hmm
you?
Yeah. So you know how we want this double bond right here because we said this is the most stable one right here,
Mm-hmm. Mm-hmm.
this one right there. Um, that's gonna be right here, right? Like we want to form that double bond eventually from here.
Mm-hmm.
From this double bond right here, and we look at A and B, which one is closer, A or B?
Oh, A then. Yeah.
A,
Okay. Okay.
yeah,
Makes sense.
A. Uh-huh.
Okay.
Right. Okay. So now to make that double bond right there, we're gonna bring in the alcohol as a base, right? That's gonna grab that hydrogen right there. The bond between the hydrogen being grabbed and beta carbon right there is gonna create a double bond right there. And that's the final answer of the mechanism. We create that double bond right there. Which if I highlight like where that came from, like this bond came from,
Mm-hmm.
in pink, that's that pink bond right there, like that.
Got it. Okay.
Okay. Okay. Now, that's SN1E1, right? This is the E1 product. They're similar in that SN1 and E1 will both form a carbocation intermediate like that. Right. Um, SN2 uses a strong nucleophile that is negatively charged and it's one step. Right. So let me make this clear. So SN1 and E1, they have multiple steps,
Mm-hmm.
right? And they will go through a carbocation intermediate, right? SN1, E1, they always form that carbon with a positive charge, carbocation intermediate. And once you have that carbocation intermediate, you could either do SN1 or you could do E1.
Mm-hmm.
SN1 is when the nucleophile attacks the electrophile, right?
And the other one's for alkene.
E1 is creating the alkene, getting the most substituted beta hydrogen, and then making a double bond there to make it the most substituted alkene, the most stable alkene.
Can you write that in the notes really quick right there?
Yeah,
The
yeah,
loadout. So
yeah,
you just have it in green.
uh-huh. SN1, nucleophile attacks electrophile. This one here, base deprotonates, most substituted beta carbon that will lead to the most stable alkene. Okay,
Perfect. Thank
for
you.
SN1 E1. And I'll send you these notes as well for you to review and the recording as well for you to
Thank you so
review.
much.
Yep. And then SN2 and E2,
This is one step.
yeah, is one step, one concerted step, meaning that there's multiple arrows happening at the same time, simultaneously. Okay.
Okay.
Mhm. SN2 is gonna substitute the good leaving group with the strong nucleophile, right? And it does that by the strong nucleophile doing a backside attack
Mm-hmm.
on the electrophile.
Really quick, if there's a
Uh-huh.
backside on the electrophile, and isn't that like kicking out the leaving group
Uh-huh.
or?
Yep, kicking out the leaving group.
Mm,
Kicking out the good leaving group. And inverting stereochemistry. Like if you had a wedge bond and you do SN2 reaction, the product is
mhm.
gonna have a dash bond.
Uh-huh.
Or if you have a dash bond and you kick out you do a backside attack on that carbon, kick out the good leaving group, your product is gonna have a wedge bond. And that's from the backside attack.
Mm-hmm.
Stereochemistry. Inverting Kara center. Okay. E2 is also one step, but it's gonna use a strong base, strong nucleophile, and those are gonna be like the hydroxide ions, OH minus, OR minus, NH2 minus, R and H minus. Like any of these strong bases here, strong nucleophiles are gonna grab or deprotonate the most. I didn't go over this one yet, but I'll go over this one after this. Deprotonate the most substituted substituted beta carbon that will lead to the most stable alkene. Okay, so let me give you an example of E2 here. Let's say that we have this molecule over here, right? And let's say that we want to use a strong base, strong nucleophile like NaOH and water.
Mm-hmm.
Okay, we have a good leaving group present, which is this right here.
Mm-hmm.
Now, this carbon here attached to the good leaving group is the substrate or the alpha carbon. Is that a methyl primary, secondary, or tertiary substrate? How many other carbons is that carbon attached to? Is this substrate carbon attached to?
Two more. That's good.
Uh-huh. So, if we look at it right
Oh,
here,
actually,
uh-huh.
no, it's attached to three.
Three.
Yeah,
This
sorry, I didn't look
one,
at the back.
two, three.
Yeah.
Yeah, this one right here as well. Yep, three. Making that tertiary, right?
Mm-hmm.
So if it's tertiary, Uh, is SN2 going to be good here or no? Like,
No.
no, right? Because it's too bulky, too crowded,
Yeah.
too much steric hindrance there,
Yes.
right? But you know how we have a strong base strong nucleophile here? We could
Hmm.
do E2 reaction. And this is the alpha carbon. We're not interested in the alpha carbon for E reactions, like E1, E2. We're interested in the beta carbons with the
Yeah.
hydrogens, right? So I'm gonna circle all the beta carbons in blue like this. This is a beta carbon, this is a beta carbon, and this is a beta carbon. Now, for the mechanism here, we need at least one beta hydrogen coming off of the beta carbon to do the mechanism. So we
Hmm.
do have at least one beta hydrogen for each and every one of these beta carbons here, right? The one that's going to form the most stable alkene, the most substituted alkene with hyperconjugation, is going to be the most substituted beta carbon, right?
Hmm.
Or the most substituted beta hydrogen. So which one would that be? Which one looks more crowded to you? Which one looks more bulky to you? A, B, or C? Another way you can think about that is like think about if the beta carbons are primary, secondary, or tertiary, and compare them that way.
I would say A is the most bulkiest.
Yeah, A is the most bulkiest compared to B and C
Yeah.
because A is coming off of a tertiary beta carbon, right? Because the beta carbon is attached to three other carbons, one, two, three. B is attached to a primary, or yeah, primary beta carbon, right? Because this beta carbon here is only attached to one other carbon, and C is attached to two other carbons, so secondary, right? So because A is the one we're interested in, I'm gonna erase the other ones. I'm gonna erase this one, and I'm gonna erase this one right here because we're not gonna focus on that to create the more stable alkene. Okay. Now, because A is the one that is the most bulky one, most bulky beta hydrogen, this NaOH here, whenever you see Na, like we said, is positive charge, but that means whatever is attached is negative charge. So the negative charge here is this OH minus ion, the
Hmm.
hydroxide ion, which is a strong base that's gonna grab that proton right there, right? Grab the most substituted beta hydrogen. The bond between the hydrogen being grabbed and carbon right there is going to move over to create a double bond right there.
Hmm.
And then if we create a double bond right here, this carbon here is gonna break the octet rule, okay, right? Because like if we don't do anything else, it's gonna have five bonds. One, two, three, four, five. That's not good. To
Hmm.
conserve the octet rule, to keep the octet rule, we have to kick out the leaving group at the same time.
Hmm.
So there's three things happening at once in E2 reaction. The strong base will grab the most substituted beta hydrogen, where the bond between that beta hydrogen being grabbed and carbon right there is going to form a double bond right here between the alpha and beta carbon,
Hmm.
and then that will kick out the good leaving group at the same time, right? Which will lead to this product right here, like that, right? This methyl group here is that methyl group right there, but the bromine got kicked out as a Br minus ion, like that, and water gets formed. H2O gets formed here because the OH here, OH minus here, grabs a hydrogen to form H2O.
Okay.
Neutral, like that. Okay. And that's E2 right there. What kind of alkene is this? Unsubstituted, monosubstituted, one of the three disubstituted, trisubstituted, or tetra substituted?
It it
Uh-huh.
looks like one. It wasn't it. That looks like dye, doesn't it?
Di? It looks like di because of these two argues coming out, but this is a little bit tricky because another way you can think about it is that these two carbons here are the two carbons of the alkene, right? Like
Yeah.
the carbons that are double bonded. How
Mhm.
many bonds are coming off of that? Those carbons in total. That is not hydrogen.
Two.
One, two, three, four.
Oh, okay.
Uh-huh. Yeah. This ring here,
Uh,
like it counts.
okay, so that is a tetra.
It is a tetra. Yep. Tetra substituted. The most stable alkene.
Okay, okay, so
Yep.
pay attention to
hmm
that. Got it. Okay, okay.
Yep. Right. That's the major E2 product. Let's say, for example, you didn't grab the most substituted beta hydrogen. Let's say you grabbed, like, this is the alpha carbon right here. And let's say you grabbed this beta hydrogen right here,
Hmm.
right? Can you describe to me what the mechanism would look like? What three arrows would happen at once here?
Like, what would happen?
Uh-huh. Yeah, what three arrows would happen at once here? Like this strong base, what would it do?
So that would grab onto the hydrogen,
Uh-huh.
and then from that, that hydrogen moves next, or like moves onto
Mm-hmm.
next bond, right?
Right here. Not
Yeah,
the hydrogen, but this bond right here. This bond right
yeah,
here. Yep.
yeah.
That bond will create a double bond between the
But
alpha and beta
and
carbon.
which then
Uh-huh.
leads that bromine to get kicked out
Uh-huh.
and to
Yep.
be the leaving group.
Yep.
And then
And that's it right there.
yeah.
Okay. Which will from this double bond right here. And what kind of double bond is this? Unsubstituted, mono substituted, di, tri, or tetra?
Oh, that double bond. That isn't that looks like mono or okay, actually,
Uh-huh. How
okay.
many?
So my question is, so you
Uh-huh.
see on that top one where it has that one sticking out, that's
Mm-hmm.
one. But the one at the
Yep.
bottom, that's turning,
That,
that would be a bond as well, right? So
uh-huh.
that would
Yep.
be
Yep.
di. Okay.
Uh-huh. And also this one as well.
Ah, see,
Uh-huh.
mm,
Mm-hmm.
okay, so then
Yeah.
that would be try.
Try.
Got
Try.
it.
Right. There's one invisible hydrogen right here, but
Hydrogen.
we don't care about that
We
one.
don't care about that
Yeah.
one. Okay,
Mm-hmm.
got it.
Yeah.
Okay.
This one's tetra because it's four. One, two, three, four. This one's tri because it's one, two,
Two,
three.
three, four.
If we don't care
No,
about the
thanks.
hydrogen.
Yeah.
Yeah. Mm-hmm.
Okay.
Okay. Which one's more stable, tetra or tri?
Tetra
Yeah. So that's gonna be our major E2 product right
into
here.
product.
That's
Perfect.
why it's very important to get the most substituted beta hydrogen, the most crowded beta
Got
hydrogen.
it. Okay, perfect. Thank you
Okay.
so
Yep.
much.
Of course, Emily, I'll send you the notes and the recording of this, and then send you and then let you know as soon as possible. Okay.
Yes, please. I
Uh-huh.
did definitely trying to purchase another lesson, but you said
Uh-huh.
you don't do Sundays, you only do Mondays, huh?
Oh, for our sessions, like tutoring sessions.
Yeah.
Yeah, so Mondays I'm really busy and Tuesdays I'm really busy as well. But I could do Tuesday night, like at like 9 p.m. Tuesday night at 9 p.m. because I get really off really late at Tuesday school.
Okay.
But I could do Wednesday and Thursday as well. What time is your exam on Thursday?
It's at 3 p.m.
3 p.m. Okay, okay. Yeah, so we could do Monday is really busy. I have like the whole day. We could do Tuesday and Wednesday. Tuesday and Wednesday.
Tuesday and Wednesday. Okay. And really quick before you go, what do you like recommend for me to do right now in the meantime? Like
Uh-huh.
just do
Yeah.
homework or again, like because I'm gonna study right now too. But
Right. Yeah, I recommend going over SN1, E1, E2 video and a practice worksheet, right? Which I will send you as well. Like what video to watch, what I learned from, and also a practice worksheet as well. Right? And
okay.
then after that, like really get to know this practice exam. Like understand that practice exam. Right? And then
Okay.
whatever is problems you're stuck on, star it, right? And then on the next session, we'll go over the starred problems.
Got it.
Yep.
Okay, perfect.
Yep. Yep. Of course,
Alrighty.
Emily.
Okay, thank you so much.
Yep. Of
Bye.
course. Bye bye.